Hello everyone! Today we're going to look into black box fuzzing. Black box fuzzing means that you want to generate inputs that, again, cover as much code and of course as many bugs and vulnerabilities as possible, but without any knowledge about the program to be fuzzed. So we're not going to look into the program code and we're not going to get any feedback from the program at hand. So, interesting question. How do we do that? Assume you have an interpreter of arithmetic expressions. And the inputs to this interpreter are indeed arithmetic expressions, as we all know and love them. And if we manage to get a very complex arithmetic expression into our interpreter, then we can actually trigger a bug. Would be nice. Can we do this with just putting together random characters? So with generic fuzzing, say in Bart Miller's style, where we're simply putting together digits and parentheses and operators, we can surely generate plenty of such inputs. Same goes if we go and mutate things. But the problem is that the largest majority of these inputs will be simply invalid. This is great for testing the error handling of the program on the test. But if you want to actually go into the functionality of the program, that is the actual computation of arithmetic expressions in our case, that is anything that goes beyond the parser, you need to come up with inputs that are valid, syntactically valid in the first place. In order to get there, in order to teach the fuzzer what a valid input looks like, well, we need a bit of help. And this help comes in the form of so-called language-based fuzzing. And the language-based fuzzer allows you to actually specify the language in question. The language meaning here the set of inputs that is valid. And by specifying the language and by actually controlling the language, this allows you to put in all of your knowledge about the program domain, about the program, about its input, and what needs to be tested. So this is the advantage of so-called language-based fuzzers, that they allow you to do all these things, putting in all your knowledge. The disadvantage is you also have to do a bit of this. The way that language-based fuzzers typically work is by having a grammar. A grammar is a specification of a language, or more specifically of a set of inputs. We are looking into so-called context-free grammars, which are very versatile and which can be used to specify almost all syntactic features of inputs. Here we do have a grammar for specifying the language of arithmetic expressions. This is practically the mother of all grammars, because this is the standard examples as we know it. So what is a grammar made of? A grammar is made of rules, and a rule tells you which symbols could be expanded into other symbols. What does that mean? We start with a start symbol, which is on the left-hand side, and then we expand this symbol into any of the expansions that are listed on the right. So a grammar consists of an expression. And an expression here consists either of term plus expression or term minus expression or a term. In these rules, we do have two kinds of symbols. We do have non-terminal symbols, which are these in angle brackets. And we also have terminal symbols, which are here without angle brackets. These are symbols which are not expanded any further. So they end the expansion and therefore they're called terminals. So, how does this whole thing work? Again, we take such a grammar and we start with the start symbol. And then in this string, which is a working term, we expand any such symbol by what is on the right of our rule. So here, start becomes expression. And now we keep on doing this again and again. An expression becomes term minus expression. If we have the choice between multiple alternatives, as in this case, we simply randomly choose one. So term minus expression, here we go. Now we have two terminal symbols, And we start with expanding term. Let a term become a factor. Now we have factor minus expression. Let a factor become int.int. Let the first int become a digit. Let the second int also become a digit. And now we can still keep on expanding these digits. Let the first digit become the digit 8. And now we expand the second digit also into a terminal symbol. So we get 8.2. So this was the left half of the expression, which we just have expanded until nothing else was left. Now we do this for the right half as well. And this is how we can get this super complex arithmetic expression as we have seen from the very beginning, simply by applying one expansion rule after another. And this is what we can feed into our interpreter. And since this is syntactically valid, we now have a chance to actually cover the entire code of our interpreter and actually also find bugs in it. So this is not limited, obviously, to arithmetic expressions. Actually, this can be done for any language as long as it's specified by grammar. And the language-based fuzzer takes such a grammar and then tests the program under test. A couple of years ago, we have done this in an almost industrial setting. We have built a fuzzer called langfuzz, which, among others, can be parameterized with a JavaScript grammar. So we wrote a JavaScript grammar and fed this into the fuzzer. And then the fuzzer happily produces JavaScript code, which then fed into the JavaScript interpreters of Chrome, of Firefox, and Edge, and more browsers. And actually, we happily found bugs in all of them. And not just one bug. So far, langfuzz has found more than 2,600 confirmed and fixed bugs in all these browsers. So if you're looking at this right now from a browser, from web browser, the reason why your browser works is, well, partially because of our work at the time. And when I say our work, it's actually not so much our work, but rather the work of one single master student at the time. This is Christian Holler. And I'd like to point out that Christian Holler also got some bug bounties with that. He netted about $50,000 in the first 4 weeks of running the fuzzer. Since I had Christian Holler and since I'm telling this story, I never had a lack of master students who wanted to work on fuzzing. So, the nice thing about such grammars is not only that you can feed them into fuzzers, but they're actually available for humans to work with. So here we have a grammar for Json. You know, Json is a simple meta language for representing structured data. And this can go into a fuzzer. So far, so good. But you can also feed it into a parser. And then the parser allows you to actually read in existing inputs in order to mutate them later and still be syntactically valid. We'll look into this later into the course. And last but not least, you can also make them available for humans. And what is it that humans can do with it? Well, for one thing, humans can actually read them and manipulate them. For instance, humans could say, okay, I want this whole thing to be probabilistic, and I want specific elements to occur less often, and I want other elements to occur more often. This is a way to exercise control about what should be tested in here. For instance, you could focus your fuzzer towards things that have recently changed, inputs that you think are particularly critical. So you actually have control, and then you feed this into a fuzzer. In this case, this is so-called probabilistic grammar. We'll look later on into how to represent this. And then the fuzzer will happily produce plenty of, in this case, JSON dictionaries within curly braces. And you can also go and do other fun stuff with that. Notably, you can add strings that you want to occur often in your inputs. For instance, if you go and say, okay, I want this particular string drop table students to frequently occur in my JSON code, then you can tell the fuzzer to actually do that. And if you tell this to fuzzer and the fuzzer takes your extended grammar, then your fuzzer will happily produce plenty of inputs with these particular strings in them. And if you are working in the security domain, this, of course, is an established way to generate attacks, to generate so-called SQL injections, in this case, where the program on the test can be fooled into interpreting commands that are part of your input, and these SQL commands, in this case, could result in specific elements of your database being deleted. Kids, do not try this at home, do not try this at work, do not try this on any machine that is owned by a third party or used for production. Your penal code has many, many ways of getting you into jail if you do this on a real production machine. Do this on your machine at home, do this in a Docker container, and do not release this to the public unless you exactly know what you're doing. Okay, so far so good about a bit of security testing. How do we actually get this into our code? Here we go. We are now in the chapter on fuzzing with grammars. And we have an introduction into grammars here. And the interesting thing is, here we have a grammar on arithmetic expressions. And the interesting thing is, how do we encode such grammars into Python? This is the first thing we need to do. Here again, we have our expression grammar. And our expression grammar here is represented by a mapping of strings into lists. And each of these strings, these are the keys of our mapping. A mapping in Python can be seen as an associative array, or as an array whose indexes are actually strings in here. So every such string, every key in that mapping is a symbol. So this is the left-hand side of an expansion rule. And on the right-hand side, we do have a list of possible expansions of the symbol, again, as strings. So the start symbol can be expanded in exactly one string, so which becomes expression. An expression is either term plus expression or term minus expression or just term. Okay? And a term becomes a factor multiplied by term, factor minus term. So every single rule of the grammar then becomes a mapping of the left-hand side towards a list of possible alternatives on the right-hand side. And with this structure, we can now actually build a simple fuzzer that keeps on expanding things until we have reached the full string without any symbols left. So I'm going to skip that, and we're going to go directly into our simple grammar fuzzer, which is here. So let me just execute everything we had so far. Here we go. And let's also get this definition in, and here we go. Great. So this is a very, very simple, almost naive grammar fuzzer, and we are looking into that. It's not the most efficient thing on the planet, actually. It's almost embarrassingly inefficient, but it gets the job done, and it fits in a few lines of code. So what does this do? A simple grammar fuzzer gets a grammar. This is it. And we have a couple of parameters where we can set the start symbol and other stuff. And we have a working string which is called term, and it starts with the start symbol, which happens to be start at the very beginning. And now what this thing does is it iterates over this term, and it keeps on expanding things while there are still non-terminals in that string. What it does is we have a function called non-terminals, which gets us a list of non-terminals contained in that string. and it picks a random symbol that we're going to expand, and we get this in here. This is almost like pseudocode. And then we fetch the possible expansions from that grammar, and we put this into a variable called expansions. So now we have a list of possible expansions. Now we randomly choose one of these expansions from the symbol that we want to expand into these expansions. And then we replace the symbol that we want to expand by the expansion. And we do this precisely once, and we assign this to new term. Later, new term gets assigned to term, and this is how we keep on expanding, and expanding one non-terminal by the next, until there's no more non-terminals left. So this is how the whole thing works. Now there's a catch, because you may actually end up with a with an endless expansion of things. So we need to put a limit to this expansion, and we do this by introducing a variable called max non-terminals, which limits the number of non-terminals that you're allowed to have in the term that we're working on. And if this number is exceeded, then we go and we try another. Then we go and retry the whole thing. We go for another expansion, again randomly chosen, until we hopefully find an expansion that actually reduces the number of non-terminals, or at least doesn't inflate the whole thing. And we keep on doing this until we have reached, until there's also a maximum number of trials here, which by default is 100. And if we, even after 100 trials, we haven't found a single replacement that still allows us to reduce the number of non-terminals in our string, then we give up and we raise an error. Okay, this is not particularly elegant, but well, it still does the job. And well, maybe you can just, if we get such an error, maybe we can just try again and try again and try again. As I said, not very efficient, but it gets the job done. So let us put this into use. So I'm invoking this with the grammar being our expression grammar. And we want the number of non-terminals to be limited to 3. And we also have a log parameter, which allows us to actually see what's going on. So let's do this. And here we see the log, then what's happening. On the left-hand side of the log, we see the rule that is being applied. And on the right-hand side, we see the result of this. So initially, we start with a start symbol and we replace it by expression. So we get expression, just in the example that we've seen before. Now we replace expression by term plus expression. This is one of the expansions that are randomly chosen. And now we have term plus expression. We replace term by factor, and then by integer, and then by digit. And here we have 6 plus expression. And now, again, we randomly is good because there's only one symbol left. Now we expand expression into term minus expression, and we keep on doing this and doing this and doing this and doing this and doing this until we reach a string which has no more non-terminal symbols left, and this is the string that we actually return. So we can do this a couple of times, actually. Let's see what we get out of here. Let's try this one, for instance. Let's just try this again. Oh, this is a very This is a very interesting string. So we have multiple prefixes, plus, minus, 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 plus, minus, plus, plus, whatever. So you can already see that there's very interesting arithmetic expressions coming out of that. And if you feed these into a calculator program of your choice, you're going to, well, not this one. If you feed these into a calculator program of your choice, you're going to test lots and lots of individual features. So here we go again, and here we go again. And yes, we get plenty of these. And if we further increase the number of non-terminals, we can even get a much more complex input. Wow, this is a beauty. Where does this start and where does this end? I think it's this one. Okay, wonderful stuff in here. So very complex expression, great for testing. We can easily do this for a number of different formats too. So here we have a grammar for CGIs, for instance. This is an encoding for strings as they are part of a URL. And speaking of URLs, here's a grammar for URLs. So let's go and execute this whole thing. So this is URLs. And as you can see here, a URL, what do we have here? A URL has a couple of schemes followed by, which in a scheme is either HTTP, HTTPS, FTP, FTPS, and we have an authority, which is a host or a host : port, or also a username together with a host. And we have a couple of hosts, we have a couple of ports, and we are being we're being rather short here because we only put in a small number of individual instances in here. And if you have that, you can actually go, okay, here comes the syntax diagram visualizing the possibilities in here. And if you have all this, you can very easily produce a number of inputs, say for a browser again, or for a URL parser. And all of these can then, no, you cannot open these. And all of these can be used to test whether your URL browser has any hidden bugs in there. And of course, you can also use grammars for what they were originally invented for, namely for producing natural language strings. Here we have done that for producing a couple of possible titles for the book, say The Joy of Fuzzing, or The Art of Fuzzing, or Principles, Techniques and Tools for Fun and Fun, or for reliability and security. So grammars give you all this big diversity in inputs, which you can all use for all kinds of purposes. And it's all in the simplest form. It is just some 20 lines of code in Python, that is. In the rest of the chapter, which I very much encourage you to read, we have we give a couple of practical hints on how to work with grammars. We're showing how to deal with, how to actually express angle brackets as terminal symbols in your grammar. We also show how to extend grammars incrementally. We also show how to express entire classes of characters such that you don't have to put in A, B, C, D, E, and the other 21 characters, so we have a couple of shortcuts here. We simply you can put in S range and C range in order to come up with ranges of characters. For instance, if you put in C range of 0 to 9, then this gives you a character range. So character range of 0 to 9 gives you all characters between 0 and 9, ASCII characters that is, or A to Z gives you all lowercase ASCII characters. We also introduce a couple of shortcuts, namely the so-called extended Bacchus-Naur form, or EBNF form, which allows you to come up with expressing that symbols are optional, or to express a number of repetitions. We do this by automatically transforming EBNF grammars into standard way of expressing grammars. And in particular, down below, there is one function which you definitely should look into when you are writing your own grammars. This is a helping function, which is called isValidGrammar. And this helper function actually runs a number of checks on your grammar definition. So it checks all the types, which is one thing, but it also checks whether for every single symbol that you use in your grammar, there also is a definition, and whether for every single thing that you define in your grammar, there's also a corresponding use. This catches lots and lots of errors in grammars and is highly recommended for you to use. Actually, I never write a grammar without also checking for isValidGrammar because, well, I easily make mistakes, and then and isValidGrammar is written such that we can actually catch them all. So this is all we have in this grammar writing stuff. Again, an example, phone numbers and other stuff. You'll find more grammars to work with in the exercises. And with that, I will be very happy to have you code your own grammars for your particular problem domain, for your particular language of inputs. And you can toy out, and you can already start toying with a simple grammar fuzzer to produce plenty of these. In the next chapters, we're going to build on that and extend this further. Notably, we're going to introduce a much more efficient way of expanding grammars. We're also going to look into probabilistic fuzzing. We're going to look into integrating generators so that is code that is automatically executed into our grammars. We're going to look into how to ensure to cover as many different aspects of the input language as possible. So this is a bit of an outlook into the next chapters. That's all for now. Thank you very much and enjoy the read. Bye bye.